Okay, so this is sort of what we've been building up to up until this point, which is just given a set of reactants, how can we predict what the products are going to be, right? Which mechanisms do they undergo? At this point, it's probably clear that there's a lot of different things that we have to consider. Okay, so this lecture is going to be kind of a nice little summary of all these different considerations that you have to make, right? Because we know that in a lot of cases, we're going to get a mixture of both elimination products and the substitution products, right? And so the question is like, what happens more? What's going to be my major product? That's going to be something that I'm going to ask you a lot. Here are two sets of reactants. Give me all the products and determine which one is the major product. Okay, so let's go through how we would figure that out. And I guess just note, it's not always going to be a mixture of substitution and elimination. There are going to be certain circumstances that only favor the elimination product, or certain circumstances that only favor the substitution product. Okay, so let's just go through step by step and how we're going to do this. So first, in terms of like what you're going to do, you're going to look at first your reagent, and you're going to classify that as either being a weak or a strong base, and either a weak or a strong nucleophile. Right, so that's going to be consideration one. Then you're going to look at the substrate, and you're going to determine which mechanism is preferred. Right, so we talked about how primary alkyl halides can't form those carbocation intermediates, so they're not going to go through SN1 or NE1, et cetera, et cetera. And then at the end, once you figure both of those out, then you can start thinking about the regioselectivity and the stereoselectivity, okay? So let's put together like this cheat sheet, okay? What you want to do is have in your mind sort of two different groups. Primary and secondary alkyl halides are going to be lumped together, and then tertiary and those allylic benzylic ones are going to be lumped together, okay? Primary and secondary are going to undergo SN2 and E2 only. So these primary and secondary alkyl halides cannot form carbocations, right? So the only mechanisms that they can undergo are SN2 and E2. For tertiary, they can undergo the SN1 and E1, but they can also undergo E2 reactions in certain circumstances. So no SN2. And we're going to lump allylic and benzylic alkyl halides into that same category as well. So we're going to consider them to behave the exact same as a tertiary carbocation. All right, so you're looking at your substrate, and you're going to be able to pare down immediately what type of reactions are going to occur. When we're looking at the nucleophile, we can lump these into different things. So remember, substitution reactions, SN2, are favorable when you have a strong nucleophile. And E2 is when you have a strong base, okay? SN1 can occur if you have a strong or a weak nucleophile. Okay, you just got to be able to form that carbocation intermediate. That's the real important part there. And then E1 reactions, I mentioned before, and this is something to keep in your back of your mind, they're the most rare. They're only going to occur when your compound is both a weak nucleophile and a weak base. Okay, so again, we can go through and we can categorize like all these different nucleophiles that we've seen as being either a weak base, weak nucleophile. So remember, these are just molecules that don't have a net charge, but they do have a lone pair of electrons to donate. We also said that any sort of amine we would put in this category as well. So I think that those aren't too terribly hard to spot. A little bit more odd is when you have a strong nucleophile, but that strong nucleophile is a crappy base, okay? These are, first of all, you have the halide ions, okay? We also have, notice what these all share in common, and that is a sulfur atom, whether or not it has a negative charge, actually. So sulfur is just not a particularly good base, but it is a good nucleophile. The other things I would add to this category are the cyanide ion, as well as the carboxylate ion. So I'll show you what I mean by that real quick. Okay, so this would be a carboxylate, RCOO minus. This is also going to be a strong nucleophile. I put a little asterisk here because these are actually considered moderate bases. They're not weak bases, but they're not strong bases at all either. For our purposes, let's just make things black and white, and we're going to lump them into the weak base, strong nucleophile category. Okay. Next, we have strong base, strong nucleophile. This is going to be like the most typical category. Usually, if you're a strong base or a strong nucleophile, you're also a strong base. So these are any sort of oxygen with a negative charge, what we call those alkoxide ions, as well as, you know, and so this is a methoxide or an ethoxide. It doesn't matter what's going on the other end of that oxygen atom. Doesn't matter how long the chain is. Same when you have these, what are called amide ions, or a nitrogen that has a negative charge. Those are going to be strong bases and strong nucleophiles. All right, and then our sort of like specialty case, these are, you know, kind of more designer nucleophiles, or designer compounds. These are going to be compounds that are weak nucleophiles but strong bases. And remember, the key here is that they are bulky. All of these are examples of bulkies. This is actually a little bit of a weird one. This is a hydride ion, which will form hydrogen gas, react with another, will remove a hydrogen off of a compound and form hydrogen gas. So it's a little, kind of a special case. All the rest of these have this one same feature, which is that they are big and bulky, right? So they're strong bases. The only reason they can't behave as nucleophiles is because they can't approach and do that nucleophilic attack very well because they're just too big and bulky, okay? So we had the tert butoxide. Remember, there are also these DBN and DBU. Seems like kind of these random ones to throw in there. The ACS loves to use those though. So when you see that DBN, DBU, you think bulky base. Okay, so now let's put these two considerations together. This chart is pretty money right here. So I guess there's kind of a lot going on. Let's try to take this step by step here. So again, we're going to say tertiary. We're going to also lump in allylic and benzylic into the same category, okay? When you have a weak base, weak nucleophile, for the tertiary, that is the only time that you're going to see the N1 and E1 reactions. Or it's the only time you're going to see an E1 reaction. And anytime you have that situation, we're going to say it's like 50-50 SN1 and E1 happening at the same time. Okay, so that's only when you have a tertiary benzylic or allylic and a weak base, weak nucleophile. Notice if it's a primary or a secondary, nothing's going to happen. Okay, the one maybe kind of asterisk I would put in there would be, for example, is when you have a potential for a rearrangement, right? So for something like this, would also undergo, even though it's primary, would also undergo the SN1 and E1 type reactions under these conditions. Same thing over here. Even though this is secondary, it would, because again, you have that potential for rearrangement. So I'm going to put a little asterisk here and say, I'm going to get rid of this. SN1 and E1 if rearranged. So again, I'm sort of trying to warn you about that. That's kind of, I think, the hardest to see. It's really easy to spot a tertiary alkyl halide. It's a little bit harder to spot one that will rearrange itself to form a tertiary carbocation, okay? But under those conditions, weak, you're gonna have a mixture of SN1 and E1 products, okay? So now let's look at the next case where we have these strong nucleophiles that can't behave as bases. Okay, so if it's a weak base, You're not gonna, but a strong nucleophile, you're not gonna have any elimination product, all substitution. With primary and secondary alkyl halides, that substitution mechanism is going to be SN2. With tertiary, right, tertiary alkyl halides cannot undergo SN2 because they're just too sterically hindered. So instead, it's going to be SN1. But again, importantly, all substitution in this case. Okay. I'm going to jump over here to this category here, strong base, weak nucleophile, because you can see across the board, it's the exact same. They're all going to undergo E2 eliminations, right? So in this case, you have this particular reagent that is a strong base. It will accept a hydrogen, but it is a terrible nucleophile, usually because it's big and bulky. So no matter what the compound is at this point, you will form E2 products, okay? If you have a strong base and a strong nucleophile, okay, so let's, I guess, just an example here, this would be like a tert butoxide. We have a strong base and a strong nucleophile, for example, the hydroxide ion. This is where you can see things are the most complicated. If it's tertiary, let's take this category here. You're only going to have the elimination product. Why is that? Because you have a strong base. Even though it's a strong nucleophile, it can't do a nucleophilic attack because of the sterically hindered tertiary site. So then this is the only place you can notice where primary and secondary differ. So right, I told you to hold primary and secondary alkyl halides together in your mind in this one category. This is the only place where they differ slightly. We're going to have a mixture of SN2 and E2. For primary alkyl halides, the major product is going to be the substitution product. That's because primary alkyl halides are not at all sterically hindered, and so they undergo substitution reactions really quickly. So that nucleophile has no problem attacking that electrophilic carbon. When it's a secondary alkyl halide, that alpha carbon is slightly more sterically hindered, so you will get some substitution product, but the main product that you're going to see is the elimination product. Okay, so this is the only place where primary and secondary differ. And I think the easiest thing is to have in your mind, primary prefers substitution, secondary prefers elimination. All right, so let's do an example. And then once you figured that out, you got to then start thinking of stereochemical considerations. And those are, of course, different for each of those reaction mechanisms. But let's go through and do an example here. Okay, so here's my substrate and my reagent that I'm given, and I'm asked to determine what are all the products and indicate which one is the major product. And I got to keep in mind stereochemistry. Okay, so first of all, NaOH. This is strong, right? So strong nucleophile and a strong base. Okay, so that means that we're thinking SN2 or E2, right? And then we're going to look at our alkyl halide. This is a secondary alkyl halide. So again, just by considering our base, we know that we have an SN2 or E2. And then once we consider the fact that it's a secondary alkyl halide, remember what does secondary prefer? Secondary will prefer, we'll get a mixture of the SN2 and E2, but E2 will dominate because of that slight steric hindrance that you have with the secondary. So once we figured that out, now it's time to think about regioselectivity. One thing I want to warn, this chart is great. Make sure that you're practicing some problems without this chart, right? You don't want to become overly reliant on these two charts here in order to figure out what's going on. So you really want to like walk yourself through that logical process. Why do secondary prefer elimination and primary prefer substitution? That should make sense to you. Okay, so now we're going to go through and we're just going to do our products for each of these different reaction mechanisms. We know it's a mixture of SN2 and E2 is preferred, but we still need to figure out what all of our products are. So with SN2, what is our stereochemical considerations? Remember, this is a stereoselective reaction because you have that backside attack, which will give you the inverted stereochemistry. So the only product that I would expect here is going to have the inverted stereochemistry from my original reactant, right? So this would be my SN2 product. And again, I'm only gonna have the one. It's not gonna be a racemic mixture like it would if it was SN1. So now for E2, and of course, E2 is kind of the pain in the butt one. E2 is way more difficult when there's only one beta hydrogen. When there's more than one beta hydrogen, it's not so bad, okay? But let's go through and look at each of these different products here. First, right, when you're figuring out E2, spot your beta hydrogens, make sure your beta carbons, make sure they actually have hydrogens on them, right? And then we can do the elimination as if each one of these was going to be removed, right? So if we got rid of that, if we had elimination when that HA was coplanar, we would have this conformation. HB was coplanar, it would be this conformation. And if any one of those hydrogens on the methyl group were eliminated, we would get the last one, right? And now once you know that you have a mixture of these, what's your consideration gonna be? Which one is the most stable? So take a second and see if you can't figure out which one of these is going to be the preferred elimination product. Should be this one here, right? Because this is 1, 2, just like this one's 1, 2, so I can eliminate that. And then trans is going to be more stable, or rather when your big bulky groups are on opposite sides, that's the more stable alkene. Okay, so then, you know, basically your problem would be, here are these two reagents, that's the consideration you're gonna undergo to arrive at, here are my mixture of products, and my major product is going to be, because this is a secondary alkene, it's gonna be the elimination product, and in this case, the most stable alkene is this one right here, okay? So it is a lot, but once you approach it in this sort of step-by-step manner, hopefully it's not too bad. This is what your challenge problem for the week is going to be, because I know that it is just a ton of work. So rather than have it be a little quiz at the end here, this is what the challenge problem is for the week. This is what we've been building up to. And there are just a ton of examples in that challenge problem. So make sure you really put in the time to do it right and understand what you're doing.